Hi everyone, I'd like to thank you all for watching this tech talk focused on how to jumpstart your Edge AI vision with Texas Instruments. I'll start off by introducing myself. I'm Reese Grimsley, a Systems Applications Engineer in the Processors Group at TI. I graduated with a bachelor's degree in electrical engineering from Texas A&M and a master's in computer engineering from Carnegie Mellon, where I took an interest in low-power systems, embedded machine learning, and distributed real-time systems. I joined TI earlier this year, and I'm bringing a fresh set of eyes to Edge AI as we take machine learning inference from higher-powered microprocessors with accelerators to more mid-range MPUs. Before I dive into anything, I want to provide, at a very high level, what I want you all to take away from this talk. You can expect to learn about our investment in having a broad portfolio of Edge AI-enabled devices, how you can evaluate those, what the recommended workflow looks like, which of our optimized neural network models we support and recommend, and what TI is doing with Edge Impulse to democratize Edge AI and lower the barrier to entry. And to those of you who've already guessed it, yes, we're especially strong on vision-based machine learning applications. Given our personal reliance on what we can see, it's no surprise that imagery is such a critical modality for making machines more aware and more responsive to their environments. Vision is crucial to a wide variety of applications like smart cameras, drones, driver assistance, automated manufacturing, and many more in places like cities, homes, hospitals, and factories. But the requirements across these applications vary substantially as well, including cost, power, compute performance, accuracy, and so on. A home appliance that estimates how long to cook your food has a vastly different set of requirements than an autonomous mobile robot with a half-dozen camera feeds. There is no one-size-fits-all here, neither in hardware nor software. We're well aware of the breadth of needs here, so TI has been investing heavily into a scalable processor portfolio to meet the needs of your application. We're hitting this from multiple angles across power usage, sensing, networking, and what we're all here for, machine learning inference, aka Edge AI, while keeping consistency in software tooling and security features across these processors. For vision applications, we'll be most focused on Sitara MPU and Jacinto processors. And our MPUs are heterogeneous architectures with a mixture of ARM A, R, and M cores to fit a variety of needs. Some of these, like the TDA4VM, also includes image sensor processors, ISPs, and deep learning acceleration DSPs to offload the ARM cores and achieve higher performance. You can get started with our processors at low cost or no cost. We host an Edge AI cloud, which is essentially a server farm of evaluation boards pre-configured for exploring machine learning inference on our processors. This helps users avoid the details of setting up their own hardware and software environment. For those of you who want to get your hands dirty, but not too dirty, our processor software development kit for Linux comes with pre-built packages for popular open source deep learning runtimes like TF-Lite, ONNX, and TVM, as well as middlewares like GStreamer and ROS to help stitch together the application inputs and outputs with the data processing. We recommend a straightforward workflow, especially to developers that are newer to this space. I'll walk through each of these one by one, but the basic idea is to select a model, refine it to your use case via retraining or transfer learning, evaluate its performance on the target to assert it performs well enough to meet your application requirements, and then add this model inference to the rest of your application that runs on the target processor. For model selection, you can of course choose to bring in your own network architecture that you're confident matches the use case, but to simplify the task, we also have a model selection tool in the cloud so you can use one of our pre-trained models. This model selection tool connects to our model zoo, which is full of popular network architectures like MobileNet and YOLO v5 for vision applications like image classification, object detection, pixel level segmentation, and more. The selection tool provides several filters to narrow down which models to consider based on task, input type, resolution, runtime engine, etc. From here, you get a performance versus accuracy comparison for the models that apply, and the best ones to select will generally be along this line that traces along the top and the right sides of the graph. We call this the Pareto line. Hovering over the points of this graph gives additional information like the accuracy, required memory bandwidth relative to the frame rate, and the number of operations necessary per inference in Gmax. This information is also available with more detail in the GitHub repo that hosts the models, but it's provided here in a more convenient graphical form. And something important to note is that while you can bring in a custom model, we've done some additional work on the ones we host to assure that they'll run as efficiently as possible in our deep learning accelerators. Not all layer types and functions that are possible in artificial neural networks will run optimally on our devices with accelerators. If your model uses an unsupported layer or function, then it may not run optimally because the device will need to run those layers on the CPU instead. Starting from one of our pre-trained models is the best way to assert that you'll get the best performance from our processors that feature accelerators. And so now that you've chosen a model, let's go back to the design flow and see where we need to go next. We'll turn to training and refining the model. This entails transfer learning to modify the model to work for a particular use case. For instance, an image classification model trained on ImageNet will know 1,000 classes to recognize. But these may not be what an application needs. For instance, a machine that determines if a banana is underripe, ripe, or overripe, or even not a banana at all, doesn't care about cars or boats. To update this model, you can use our Edge AI Model Maker tool to retrain the model on a new dataset. It'll change which outputs to recognize while retaining knowledge about general image classification gained from the massive 1,000 class image set, but dial in on your specific use case. And during this process, we can also do post-training quantization to convert the model weights to integers, which can be processed far more efficiently. All this requires is a couple data points from your dataset to help calibrate the model in its new quantized form. Now that we have a model that's trained for our application and quantized to take advantage of the deep learning accelerators, we'll evaluate the model on the target processor, which can be on your own EVM or on one in our Edge AI cloud, but we'll focus on the cloud for now since you can try that today at zero cost. In addition to the model selection tool in the cloud, you can evaluate model performance from here as well. These pre-configured processor evaluation boards host Jupyter Python notebooks that can be used for testing models and understanding their performance capabilities. That can include models taken directly from the Model Zoo or your own custom models in the preferred runtime engine. The benchmarking tools included here can show things like DDR usage, CPU and accelerator load, frames per second, and latency. These are also a great source of starter code, including the, albeit minimal, configuration parameters for devices with accelerators. For running evaluation on the EVM itself, the SDK comes with the basic libraries for running inference, but requires some additional setup to enable all of the additional benchmarking tools and out-of-box demos, those of which can be easily reconfigured to run your own custom model. To see how to do this on your own EVM, please refer to the documentation for the processor SDK for Linux on Edge AI. Assuming the performance is to your liking, it's time to get it onto the processor and include it in the rest of the design. Our software tooling is intentionally hardware agnostic. We support standard runtimes and middlewares, so the rest of your application can be developed alongside these model preparation steps. Porting to the processor requires little effort. You compile the trained and quantized model to the target with our tools on an x86 host PC, change a couple of lines to activate the accelerators, assuming they're present on the device, and go. You don't need to know anything about the intricacies of the accelerator, even if you use a model that isn't 100% optimized for that architecture. The compilation tool will handle splitting the model between CPU and the TI Deep Learning Accelerator as needed. In addition to designing these processors and tools for Edge AI, TI also partners with third parties to democratize the technology, as we know it goes beyond what we ourselves can directly develop and support. We've recently partnered with Edge Impulse to make the best of both of our offerings. Edge Impulse can help you get off the ground even faster with your model, since they've done so much great work to have a toolset for data acquisition, labeling, manipulation, model training, and preparing for the target. This vastly simplifies the recommended workflow I've shown. Edge Impulse will be first supporting the TDA4VM processor, but please stay tuned. Edge Impulse will also be including their own stock models and providing support for our optimized models of YOLO v5, MobileNet, RegNet, EfficientNet, and a few others, which all take full advantage of TI's accelerators. We also work with third parties that have application and in-equipment specific expertise to help those who want an expert's knowledge both on the application and integrating with our hardware when building the system. For example, we partner with companies like Ignitarium and RidRun to help developers accelerate their workflow. I'd like to show a couple of demonstrations from them. We also have a demo from within TI that's especially interesting because it adds millimeter wave radar to the mix. This can do imaging based on 60 GHz or 77 GHz radio waves, which can help mitigate issues that camera-based sensing has, like robustness to low light conditions and obscure conditions, while providing ranging without needing a stereo vision solution. And now fully wrapping around to where we started, this talk covered our commitment to a scalable portfolio for embedded machine learning, the basic design flow we recommend, how you can evaluate at no or low cost using our cloud tools and EVMs, how you can find and prepare a model for inference on our processors, and what TI is doing to democratize Edge AI, including our partnership with Edge Impulse moving forward. I want to reiterate that TI is investing in this space. We're confident in the future of embedded machine learning and recognize the importance in having a broad range of machine learning capable embedded processors. With that said, I'd like to call my listeners into action. We love seeing what creative ideas hobbyists and customers have. We've seen many already on the public projects for Edge Impulse, and we're excited for what the future holds as Edge Impulse and TI team up. Since the TDA4VM is the first processor to be supported on their platform, we'd recommend purchasing one of the starter kits from ti.com. There's a link on the next slide. If you find yourself running into issues, please don't hesitate to reach out for help. You can reach our engineers on e2e.ti.com and the Edge Impulse community at forum.edgeimpulse.com. Thanks for your time and happy hacking!